The objective of this experiment was to see how changes to the product and reactant concentrations affected chemical equilibrium. The first reaction we looked at contained the equilibrium net ionic equation stated: Fe plus aqueous plus SCN negative aqueous to Fe SCN plus 2 aqueous. It is first noted that the Fe plus 3 and SCN negative ions are clear and colorless, and the Fe SCN has a light red color. Equilibrium between these was then established by mixing FeNO3 with KSCN together because they contained these ions from equilibrium. Once they were mixed, it created a deep red color. This mixture was then diluted with water, which turned the color to be a dark red-brown color. So at equilibrium, the color was a dark red-brown. So the first stress applied to a sample of the solution was placing it in a hot water bath. Because heat was being added to the product side, based on Chatelain's principle, this is an exothermic reaction, which would cause a shift to the left in equilibrium. Our experiment proved this because the solution turned from a dark brown color to a light red, meaning that the product side of the reaction has less than it started with, which explains a lighter color to maintain equilibrium and a shift to the left, making it an exothermic reaction. The second stress applied was adding more FeNO3 to the solution, which increases the concentration of this ion on the reactant side. Based on Chatelain's principle, because more reactant is being added, we should expect a shift to the right for equilibrium. By doing this experiment, we saw a change in the color from dark red to an even darker shade of red-brown, meaning there was more product being formed in order to maintain equilibrium, which supports a shift to the right. The third stress was increasing the amount of KSCN in the solution. Like before, when we added more of the reactant FeNO3, we should expect a shift in the right based on Chatelain's principle. Our experiment supports this because we observed a color change to an extreme dark red, almost a complete shade of brown, which does indeed follow a shift to the right. The last stress that was being applied was adding AgNO3 to the solution. It should be noted that neither the Ag plus or NO3 minus ions are in the equilibrium equation. So, from the lab manual on page 39, compounds containing nitrates are soluble. So if AgNO3 was reacted with, let's say, an SCN negative ion, we should expect the ionic equation to look like this from the reaction. With Ag plus aqueous, because it's soluble, plus NO3 minus aqueous, also soluble, plus our ion from above, SCN negative, aqueous, which would then go to Ag SCN solid, plus NO3 minus in the aqueous form. As we can see, a solid would be formed with the SCN, and the concentration of SCN negative would then decrease. When this is added to the equilibrium solution, there would be a decrease in concentration on the reactant side of the equation. So by Chatelain's principle, this would cause a shift to the left in equilibrium. So if we decrease the concentration on reactants, we'd expect a shift in the left in equilibrium. In our experiment, we witnessed the solution change to a white color that was cloudy from the dark red-brown color. Because this occurred, it proved that there was a shift to the left, meaning because the precipitant was white and not red, the AgNO3 did indeed react with one of the reactants, decreasing their concentration, which correlates with a leftward shift. The second reaction that we dealt with had the equilibrium equation of CO H2O 6 plus 2 in the aqueous form plus 4Cl minus, also aqueous, 2 COCl4 minus 2 plus 6 H2O in the liquid form. To reach equilibrium for this equation, we first combined solid cobalt chloride with deionized water. This solution had a pink and light red color, and that was for this part of the reaction. Then drops of HCl were added, and this created a blue colored solution from the original pink and red color, which was for the COCl4. The first stress applied to the solution was being placed in boiling water. When we did this experiment, the solution turned to a darker shade of blue. This means that there is a higher presence of COCl4 -2 ion in the solution because it was of the color blue. The darker shade of the solution means that there was a shift to the product side, which is a shift to the right in equilibrium. Based on our results, Chatelain's principle states that when the temperature is increased in a reaction and there is a shift to the right in equilibrium, then the reaction is endothermic. The second stress added was placing the original solution into an ice bath. Based on our knowledge from the first stress being applied, we should still expect this reaction to be endothermic. So from Chatelain's principle, when heat is being removed in an endothermic reaction, there would be a shift to the left in equilibrium. Our experiment did indeed prove this shift to the left because the solution turned into a light purple blue color from the original blue, which means that there was more of the COH2O6 plus 2 ion present in the final solution and matches a leftward shift in equilibrium for an endothermic reaction. The final reaction that we looked at had the equation HCO3 minus aqueous 2 CO2 gas plus OH minus in the aqueous form. To establish equilibrium, saturated sodium bicarbonate was mixed with an indicated solution for this ion, which was bromothymol blue. The mixture showed a blue-colored solution, which indicates that the pH was above 7.3 and it was a basic solution. Then HCl was added to the solution. There were bubbles that formed, meaning that there was a gas present, which makes sense because CO2 was in our equation, as you can see here. And the color changed to a yellow-green. This indicates that the pH is now less than 7.3, which indicates that it was a more acidic solution, which then correlates to the HCl being added because HCl is a strong acid. The stress being applied to this solution specifically was adding a vacuum aspirator, which removes the gas in a present solution. In our experiment, the gas being taken out was CO2. Using Chatelain's principle, because the gas is being removed from the product side, we should expect a shift to the right in equilibrium. to make up for the lost stress. When we performed this experiment, we witnessed the yellow-green solution bubble a little bit as the gas was leaving, and the color then turned to a light blue, which indicates that the solution is back to the more basic solution, but it still has some acidity left over because the solution was not 100% the same shade as before the HCl was added. So this supports a shift to the right in equilibrium because we saw a lighter shade of blue as the final product as CO2 was taken out of the solution.